So chapter 4, in some sense, is a short chapter because there's only one practice test and not two. So everything we need to do for chapter 4 is going to be contained in this one practice test, and the test will be kind of 1 week from the day we do this in class, in some sense, or the day we review chapter 4 in class. I typed up some stuff on these problems, which actually I've done this video and was kind of annoyed at myself that I had this stuff typed up for some other problems, but I'm just going to live with it. For this problem, I was happy that I typed this up some stuff, and the next problem I wasn't so happy the way I wrote it. Anyways, problem 1, there isn't any calculus or algebra to do. It's just understanding what the concepts are. It's understanding the concept of an absolute maximum and an absolute minimum. An absolute maximum for a graph is the point that is absolutely the highest. There's a point on the graph that, if there's a point on the graph where there isn't any point above it, it's the absolute maximum. And these 2 points right here, above those points, there's no points above those. So for this function and this particular graph, I would consider these 2 points as the absolute maximums. When we did this in class, or on my video, I didn't quite write my answer for the absolute maximum like that. What we did is we would say there's an absolute maximum of, and we take the y-coordinate of those points that are higher than any other point, and write it down next to that y, which occurs when x equals, and then we write the x values of those 2 points that are absolutely the highest points on the graph. The next thing I'm asked to find is the absolute minimum. And the absolute minimum is the point that's absolutely lowest on the graph, that there isn't a lower point. And that's going to be the absolute minimum down here, because there isn't any point beneath that point. This point 0,4 that I marked off is kind of a distractor. The point 0,4 is considered a relative minimum, which means relative to points close to it, it's the lowest point. But this point 0,4, so it's relative to the points close to it, it's lower than any point close to it, but it's not absolutely the lowest point on the graph, because that point is lower than it and makes it not an absolute minimum. So that point's a distractor. When I go to write my answer for the absolute minimum part of this, once I identify the point that's the absolute lowest, I separate the x and the y. I'm going to say there's an absolute minimum of y equals, and I'm going to take the y-coordinate of that point, which is -4, which occurs when x equals, and I'll take the x-coordinate of that point, which is -2. It's actually the third time I did this problem because I keep messing up the video. I'm just not happy with what I'm saying. At some point, I'm just going to live with it, so I think this is going to be my last go at this video. So hopefully I do a decent job at the rest of this. Problem 2, when you get to your test, will look like this. It'll say to find the absolute maximum and the absolute minimum of the function under the given interval. And I think I'm going to ignore what I have written and just do what I feel like doing. So in order to do this, I need to, for this function, create a table of values, and from that table of values, find the absolute maximum and absolute minimum. In the top of my table, I'm going to put x equals 0 for the 0 that's written there. At the bottom of my table, I'm going to put 4 for the 4 that's written there. So I'm only looking at this function between x equals 0 and x equal to 4. These are candidates for the absolute maximum and the absolute minimum. The only other candidates for the absolute maximum or absolute minimum are values between 0 and 4 where the derivative is equal to 0. So I'm going to take the derivative of this function. The derivative of 2x cubed is 6x squared. The derivative of minus 54x is minus 54. After finding the derivative, I'm going to set it equal to 0. When I have an equation that has an equal sign, or a problem that has an equal sign and a common factor that doesn't have a letter, I can divide everything by that common factor as long as it doesn't have a letter and not destroy my solution. So when I'm going to find any other values for this table, I find the derivative, I set the derivative equal to 0, and I do the algebra necessary to get the values of x that make the derivative equal to 0. This function had some big numbers, but there was a common factor that I could factor out. After I divided out that common factor, the numbers are smaller, but I haven't found the numbers for my table just yet. I'm going to factor that x squared minus 9, and then I'm going to set the factors equal to 0. And I'm going to take any answers to where the first derivative equals to 0 that are in between 0 and 4. I'm supposed to find the absolute maximum and absolute minimum under the given intervals 0 to 4. When I go to figure out what value of x relates to the absolute maximum and what values of x relates to the absolute minimum, I'm only allowed to look at x's between 0 and 4. When I did the calculus and found the values of x that make the first derivative equal to 0, I got two values, but only one of them is between 0 and 4. So I'm going to create a table that has the 0 and 4 that were given, and the 3 that's a value that makes the derivative equal to 0 that's in between 0 and 4. Now for each of these values in the x column, I'm going to find a y. And I find y's by going to the original function. So the first y I'm going to find, I'm going to go to the 2x cubed minus 54x, and I'm going to change the x to 0. I think I get 0 when I do this. Let me do this real quickly. Do 2 times 0 cubed minus 54 times 0, and I get 0. I'm going to do the same thing for 3. I'm going to do 2 times 3 cubed minus 54 times 3. And get negative 108. And the same thing for 4. Do 2 times 4 cubed minus 54 times 4. And get negative 88. These are the only candidates for the points that are absolute maximums or absolute minimums. The point that has the largest x value, y value should I say, is going to be the absolute maximum. And 0 is the biggest of these three numbers, so that point 0, 0 is where the absolute maximum is at. The point that has the smallest y value is where the absolute minimum exists, and any point that has a y that's smaller than the biggest and bigger than the smallest is a neither. This is neither an absolute maximum or an absolute minimum. So let me answer the question, then show you how to check on your calculator. So for this problem, I'm going to say there's an absolute maximum of y equal to 0, which occurs when x equal to 0, using that first point. Now I'm going to do the second point and do an absolute minimum. I'm going to say there's an absolute minimum of y equal to negative 108, which occurs when x equal to 3. I'm absolutely done. I didn't have to graph this at all. But if I wanted to, I can do this whole problem on my calculator. To confirm this answer using my calculator, I can turn my calculator on and graph the original function, 2x up arrow 3 minus 54x. Change my window. For my x's, I need to go from 0 to 4. Smallest x was 0, biggest x is 4. For my y's, my y min needs to be less than negative 108. If I made it exactly negative 108, you might not see the bottom of the graph so well. I'm going to make my y min negative 120, just so that's not at the very bottom of my screen. My my y max needs to be bigger than 0. It needs to be 0, but it's probably better to make it bigger than 0. I'm going to make it 10 just so this absolute max isn't at the very top of the screen. Now I'm going to graph, and you'll be able to see. This, I believe, is the point 0, 0 is where the absolute max was. This is the point 3, negative 108, where the negative 108 where the absolute min was. This is the point 4, negative 88, which is neither. This point's neither because there's a point lower than it and there's a point higher than it, so it's not the absolute max or the absolute min. I could get the y values by just going second in table and look next to negative 3. Oops, next to 0, I see 0. Next to 3, I see negative 108, and next to 4, I see negative 88. So I've confirmed all the values in my y columns, and I confirmed that this is the maximum and that's the minimum. I feel real good about my work. I'm going to do the same thing for problem 3. Same question, find the absolute maximum and absolute minimum. So I'm going to make a table, and in the x column I'm going to put negative 2 and positive 2, which are the x values that were given. And I'm going to find the y values in a second. I might have to add another number to that table, and the number that would be added to the table is any critical number or any value that makes the derivative equal, first derivative equal to 0, that's between negative 2 and 2. So in order to fill up this table with numbers, I need to find this derivative. And I'm going to find this derivative by using the product rule. The derivative of x times e to the x is going to be x times the derivative of e to the x plus e to the x times the derivative of x. Here, the x is going to stay x. E to the x is its own derivative. The derivative of e to the x is e to the x times the derivative of its exponent. Its exponent has a derivative of 1. Technically, the derivative of e to the x is 1 e to the x, but I'm not going to write the 1. And then to the right of the plus sign, I get e to the x times the derivative of x. The derivative of x is 1. It's going to help if I write this times 1. Now I'm going to pull out a common factor of e to the x. So there's an e to the x, there's an e to the x. I'm going to factor out that e to the x. When I factor out that e to the x, I'm going to be left with an x plus 1 that goes inside my parentheses. To get the critical numbers, or the values that might go in this x column, I'm going to take the derivative and set it equal to 0. Because I've already factored the derivative, I can just take the two factors separately and set them equal to 0. E to the x can never be 0, so this doesn't give a solution. And when you set x plus 1 equal to 0, you get x equal to negative 1. If x equaled negative 1 wasn't in between negative 2 and 2, I would ignore it. But because it's between negative 2 and 2, I'm going to include it in my work. So now I have my x's nailed down. I need to get my y's so I can figure out which one of these is the max or the min. So for each x, I need to get a y. The first x I see is negative 2, and I'm going to plug a negative 2 into the function and go f of negative 2 equals negative 2e to the negative 2. And that I'm going to write as negative 2 over e squared. This is the proper y, but when I go to figure out a maximum or a minimum, I'm not going to be able to tell if this is a maximum or a minimum until I pull a decimal out for it. So I'm going to do a decimal for negative 2 over e squared, and I get, I'll do it in a different color, I get negative 0.27. The next value I'm going to get a y for is negative 1. I'm going to go f of negative 1. And I'm going to put negative 1 in for both of those x's. I'll go negative 1 e to the negative 1. That's the same as negative 1 over e to the first. And that's negative 1 over e. I'm going to find a decimal for that by going negative 1 divided by, and then second, and then the divide key to just get an e by itself without an exponent. This is negative 0.37 if I round to 2 decimals. The last thing I'm going to do is get a y for x equal to 2. Do f of 2 equals to 2, and then e squared. That doesn't have a negative exponent. It's written in a decent form. And let me find a decimal equivalent for that. To 2e squared is equal to 14.78 for lack of a better number. Now I stare at the numbers in the y column. It's real easy for me to see the maximum. This right here is the biggest y, so this point right here is going to correspond to the absolute maximum. Between negative 0.27 and negative 0.37, negative 0.37 is smaller. This point right here is going to be the absolute minimum. When I go to write my answer, I'm going to say there's an absolute maximum of y equal to 2e squared, which occurs when x equals to 2. And I'm going to say there's an absolute minimum of y equals negative 1 over e, which occurs when x equal to negative 1. Real quickly, I'm going to pull out my calculator and make sure that this answer makes sense by graphing the function x e to the x in a window that has x min negative 2, x max 2. And I'll talk about the y's, and I'm actually going to have to do a couple little things with the y's. So let me enter the function x and then second e to the x. Make my window go from x min of negative 2, x max of 2. My y min has to be less than negative 0.37, like negative 1, negative 5, negative 10. I'm just going to make it negative 5. And my y max needs to be bigger than 14.78. I can make it 15. I'm going to make it 20. When I do this graph, I'm going to be able to see the absolute maximum very well, but I'm not going to be able to distinguish these points. So I'm going to hit graph right now, and you'll see that the graph really doesn't show up very well in this part of the screen, but I can absolutely tell that the far right point, which is the point 2, hopefully 2e squared, is the absolute max. Let me check the y's on these points real quickly. But from this window, I feel good that this is the absolute max. Let me do second in table. Look next to 2, and I see 14.778, which is kind of that. I feel good about this point completely. I have the same x, and the decimal equivalent is the same. Next to negative 1, I see something that has basically that decimal equivalent. And next to negative 2, I see something that has that decimal equivalent. I can't tell from my graph that this point right there at x equal negative 1 is the absolute minimum. And in order to see that this is the absolute minimum, I have to really condense my window in terms of the y's. I need to make the y's really small. And when I do that, I'm not going to see the absolute max anymore, but I'm done. I know the absolute max is okay. To make sure that my absolute minimum is right, I need to make my y's really small. Maybe if I make a y really close to this, like negative 0.4 to maybe 0 would be okay. Let me try y min of negative 0.4, which is really close to that y value. And then I need a y value that's close but bigger than this. Negative 0.25 would be fine. I'm just going to do 0. And this will show real distinctly what's happening. Here, there's the point x equals negative 2, comma, negative 0.27. There's the point x equals negative 1, comma, negative 0.37. Now, in that really focused window, I can tell that I'm good, that that point is actually the absolute minimum. All right, so I'm going to call that problem done. And the video's getting ready to hiccup, so I'm going to hit pause real quickly and start the next problem on the new. All right, so you're guaranteed to get a question like number 4 on your test. And the only thing I'm going to do when I create your question on the test that's kind of the sister problem to this is I'm going to change that number. Every other word's going to be the same, so we don't need to get too sophisticated in solving these. We'll just kind of just go through it, and it's going to be just like you need to do, other than your numbers are going to be slightly different. So this problem talks about a campground owner. He has 100 meters of fencing. He's going to make a rectangular region he's going to enclose that's bordering a river, and he only needs to build 3 sides of fences. The river is not going to be a fenced side, and of the 3 sides, we're going to call the widths W, the lengths L, and it says make W the side of the fence that's perpendicular to the river. I don't know that I read that so well, but I understand this problem well enough. You can read through this problem if you need to understand it a little bit better. But here's kind of what the campground owner is doing. He has a river, and he's going to build 3 sides, 3 lengths of fence in some sense. And the sides that are perpendicular to the river, I'm going to call W, are the widths. And the side that's parallel to the river, I'm going to call the lengths. That's a diagram of what the campground owner is going to do. I'm supposed to write an equation for the length of the field. That means with the information that's contained in the problem, create an equation that's solved for L. And it's actually kind of easy to do. What I'm going to do is add up the 3 sides that the farmer's building, or the campground owner's building, and it's going to equal to the 100 meters of fence that he has. So the campground owner is going to build 1 length and 2 widths, and those 3 sides of fence are going to add up to the 100 meters of fencing that the farmer has. To answer question A, I'm just going to solve this for L by minusing 2W from both sides. The answer to question A, an equation for the length of this field, is the length equals negative 2W plus 100. Part B wants me to write an equation for the area of the field. Well, this field, although the farmer's only building 3 sides of fence, is ultimately going to be a rectangle that has a length and a width. And the area of any rectangle is length times width. So the region that he's building is going to have an area of length times width. In order to answer question B, I need to take the L and change it to negative 2W plus 100. So I'm going to say the area is negative 2W plus 100 times W. I'm going to clear the parentheses and call this my answer. I'm going to say area equals, and I'm going to go negative 2W times W, which is negative 2W squared, and then 100 times W plus 100W. That's the answer for part B. Part C says make an equation for the domain. Find the domain of this area equation. Super easy to do. It tells me the domain needs to be of a form some number is less than or equal to width, and the width is less than or equal to some number. I know that the width has to be, it can't be less than 0. So the smallest the width can be was 0, because you can't have a negative width. The maximum the width can be is also easy to figure out, and that's the number that's going to go after this next less than or equal to sign. The campground owner has 100 meters of fencing. He's going to build 2 widths. If I take that 100 and divide it by 2, that tells me that the width can't be more than 50, because like if you tried to build widths are 60 each, that would require 120 meters of fencing when he only has 50. So this is going to be the domain for this function. Done with part C, moving on to part D. Part D says find the value of W leading to the maximum area. Hint, make a table, put the domain numbers along with any relevant critical numbers in the X column and solve like the last few columns. So what I'm going to do is follow that hint. I'm going to make a table. The X column is going to be the width, because the widths are in the X position, and the Y column is going to be area, or the A's, because the A in the equation's in the Y position. And I know that the smallest width is 0, the biggest width is 50, and there's got to be some width between it that probably is optimal. And in order to find the value where it might have a maximum, I'm going to take the area equation that we developed in part B, which is that equation there. I'm going to take its derivative, which is going to be negative 4W plus 100. I'm going to find the critical numbers by taking that derivative and set it equal to 0. I don't have to factor because there's not a square. When I go to solve this, I need to get the numbers on one side, the letters on the other. And when I do that, I get W equal to 25. So what I'm going to do is find the absolute maximum, the value of W that gives the absolute maximum for this particular rectangular field. What I have right now is a table of, in some sense, X values. For each X, I need to get a Y. And I get the Y by going to the original function before I took the derivative, and I'll plug those numbers into the original function. So I'm going to go and find out what the area is when the width is 0 by plugging 0 into the area equation. I can do that on my calculator. I probably really don't need my calculator because I know that that's 0, but let me do that anyways real quickly. I'm going to go -2 times 0 squared plus 100 times 0. And this gives me 0. This says if the width is 0, the area is 0. I'm going to do something similar with the 25. I'm going to go find the area if the width is 25. Go area equals -2 times 25 squared plus 100 times 25. So -2 times 25 squared plus 100 times 25. This says when the width is 25 meters, the area is 1,250 square meters. And then lastly, I'm going to plug 50 in and go -2 times 50 squared plus 100 times 50. So -2 times 50 squared plus 100 times 50. And this says if the width is 50 meters, the area is 0. Question D wants to find the value of the width that gives the maximum area, and the value of the width that gives the maximum area is 25 meters. So my answer to part D is going to be the width, the optimal width is 25 meters. So let me just scribble this here. So I'm going to go to width equals 25. I'll do an M for meters. Part E wants me to find the length that gives the maximum area. I'm going to use the formula length equals -2W plus 100 that we created on the last sheet of paper doing part A. And into that equation, I'm going to plug 25 for the W. So I'm going to get length equals -2 times 25 plus 100. And that's going to come out to 50, but I'll do it on my calculator because I like that. -2 times 25 plus 100 gives me 50. The answer to part E is the length is 50 meters. And part F wants me to do the area. One way to do the area is just use the length times width formula. The maximum area is going to be the length times the width. In this problem, the length is 50 meters. The width is 25 meters. And if on my calculator I do 50 times 25, I get 1,250 for the maximum area. And the units for the area are going to be square meters. I already had that number there, but I pretended I didn't know that. So that's going to be everything for this monstrous problem that has to be worth a lot of points on the test. There's how many parts are there? 1, 2, 3, 4, 5, 6 parts. Even if the parts are worth 3 points each, that gets to be worth 18 points. So it's a big, big pointed question on the test. It shouldn't be super hard to do. And again, when you get your test, the only thing that's going to be different is that number is going to be changed. All the instructions, all the computations are going to be the same, except every place where I have a 100, you're going to have whatever number your particular word problem has. So problem 5 is another one where I wrote a bunch up. I typed a bunch up to make it easier for me to lecture. I'm just going to try to deal with what I have there. Hopefully I can live with it. At one point I thought it was the best thing in the world to do, and now I'm not so sure. So anyways, problem 5 on the test is going to look a lot like this, except it's not going to have a couple of these parenthetical comments. What it's not going to have is this, and it's not going to have that, but everything else is going to look the same. So there's not too much on here that's I added. So it talks about a clothing manufacturer, a company that makes t-shirts that sell for $10. It gives me a price-demand equation. The price-demand equation is demand based on the price is 40 minus 3p, where DFP is the number of t-shirts sold at price P. For instance, if I put 1 in for P, I'd go D of 1 equals 40 minus 3 times 1. That's going to be 37. This would say if this company showed t-shirts for $1, they'd sell 37 t-shirts. Most of the word problems in this elasticity section, the numbers aren't so realistic in terms of if you try to work the equations, they don't make a lot of sense. But to get realistic equations, the algebra, the calculus got so ugly, I just kind of lived with it. So I'm going to do all the work and understand that in the real world, the functions aren't this simple. But I tried to make the functions simple enough to make the algebra simple. Part A says compute the price elasticity function, and this formula is going to be given on the test. So the price elasticity function, E of P, elasticity based on the price, is a fraction. The first thing in the numerator is negative P, and then there's a times sign. And after the times sign is the derivative of the demand function. This demand function is 40 minus 3p, and I'm going to find its derivative, and that's what I'm going to write in the numerator next to the p. The derivative of 40 is 0. The derivative of minus 3p is minus 3. The derivative of the price elasticity, the derivative of the price demand function is negative 3. That's what I'm going to put in the numerator next to the negative p. So the negative p came from the formula, and then the negative 3 came from the derivative of the demand function. And then in the denominator, you get that price demand function, 40 minus 3p. This is actually an adequate answer for part A, but I'm going to improve that numerator, because in the numerator, the two negatives will multiply out to be a positive, and I can write the 3 first and the p second. So I'm going to say my price elasticity function is 3p over 40 minus 3p. For part B, it says compute E of 10. That's just simply plugging 10 in to the p. So E of 10 is going to be 3 times 10 over 40 minus 3 times 10. I can do that without a calculator. This is going to be 30 over 40 minus 30, which is going to be 30 over 10, which is going to be 3. My answer to part B is going to be the E of t, E of 10, is equal to 3. Now I'm asked, at a price of $10, is demand relatively elastic or inelastic? If the E is greater than 1, the demand is relatively elastic. If it's less than 1, it's relatively inelastic. And if it's 1, it's perfectly elastic. This E is 3, which is greater than 1, so I'm going to say the demand is relatively elastic. So for your test question, your answer for part C of this question is either going to be relatively elastic if the answer to part B is some number bigger than 1, and it's going to be relatively inelastic if your answer to part B is less than 1. Because my part B is 3, which is bigger than 1, I say elastic. Lastly, how much would the demand change if the price of shirts was raised by 25% to $2.50? I simply just take this 25%, make it a decimal, multiply it by 3, and when I do this, I get 0.75. That's a decimal. I need to change it back to a percent. That's going to be 75%. And what this tells me, this 25% price increase is going to cause a 75% decrease in demand. As prices go up, demand has to go down. So that's everything for number 5. Now we'll move on to an ugly part, this implicit differentiation. Students do bad with implicit differentiation. Let me just try to walk through problem 6. So I'm going to find dy dx by doing implicit differentiation. First I'm going to do the derivative of x squared. The derivative of x squared is 2x. Then I'm going to find the derivative of 4xy. And to do the derivative of 4xy, I need to do the product rule. I need to go 4x times the derivative of y plus y times the derivative of 4x. So I'm doing the derivative of 4xy. There's multiplication, so I need the product rule. I wrote down in red what the product rule tells me to do. So the first piece says take 4x times the derivative of y. The derivative of y is 1. When we're doing implicit differentiation, anytime I take a derivative with a y, I tack on a dy dx. So the derivative of y is 1 dy dx. And then plus y times the derivative of 4x. The derivative of 4x is 4. And then to the right of the equal sign, I need the derivative of 5 because that 5 is a constant and it doesn't have an x or y. Its derivative is 0. Technically, I've done all the derivative taking I need to do. Now I just need to clean this up. I'm going to write this as 2x plus 4x dy dx plus 4y equals to 0. I need to take this and solve it for dy dx. In order to do that, I'm going to minus 2x and minus 4y from both sides. On the left side, when I do that, I cancel out the 2x, I cancel out the 4y. I'm left with 4x dy dx. And on the right side, I get negative 2x minus 4y. Now I'm going to solve for dy dx by dividing everything by 4x. On the right side, to be safe, I'm going to make 2 separate fractions. And if I do that, I can't mess up when I reduce. If I don't do that, I can mess up when I reduce. On the left-hand side, the 4x's will cancel. I have the dy dx that I'm looking for. And on the right-hand side, the first fraction, I'm going to reduce negative 2 over 4 to negative 1/2. And I'm going to cancel the x's. The second fraction, I'm going to cancel the 4's, and I'm going to be left with y over x. This is a perfect answer for what dy dx is equal to. Another thing that I could have done, on the right-hand side, I could have taken this minus 2x minus 4y, and instead of writing each one separately over 4x, I could have wrote them all over 4x. That fraction reduces, but I'm hesitant to reduce it because a lot of students would make mistakes if they did that. Both of these answers are completely correct. Turns out each one of these numbers you can divide by 2. You could also write, if I divide all those by 2, you can say dy dx equals, that divided by 2 is going to give me negative 1x. That divided by 2 is going to give me negative 2y. This divided by 2 is going to give me positive 2x. That would also be an alternatively good answer for problem 6. I can even factor out a negative 1 from the numerator. If you got any of the 3 answers I have boxed or something equivalent to one of those, that's completely fine. That's all I want to say about number 6. That's a tough question. Problem 7 wants me to do implicit differentiation again. So first I'm going to take the derivative of 3y squared. The derivative of 3y squared would be 6y. But because I took a derivative of a letter that had a y, I'm going to tack on a dy dx. Next, I'm going to take the derivative of xy. There's multiplication, so I need to use the product rule. I'm going to take x times the derivative of y plus y times the derivative of x. When I do this, I bring down this plus sign. X is going to be x. The derivative of y is 1. When I take the derivative of y, I tack on a dy dx. Bring down this plus sign. Y is y. The derivative of x is 1. and I don't need a dy dx, so I took a derivative of an x there. To the right of the equal sign, that 8 has a derivative of 0 because it's a constant. Let me clean this up. This is going to be 6y dy dx plus x dy dx plus y equals to 0. I need to keep the letters that have the dy dx on the left-hand side, and the terms or the letter that doesn't have a dy dx I need to move to the right side. So I can rewrite this as 6y dy dx plus x dy dx equals to minus y. And now I'm going to treat this dy dx as a common factor, and I'm going to factor out a dy dx. On the left-hand side, I'm going to write the common factor of dy dx, and then I'm going to be left with a 6y plus x to go in a parentheses equals my negative y. My goal is to solve for dy dx. Because this 6y plus x is being multiplied by the dy dx, I'm going to divide both sides by it. On the left-hand side, that 6y plus x is going to cancel. I'm going to get a dy dx. And on the right-hand side, I'm going to get a fraction that can't be reduced. If you try to reduce this, you're probably going to make a mistake. I don't know that it can reduce. So that's going to be my answer to 7. And I can't write or because there isn't an or that I can think of anyways. Just a few more problems left. This is feeling like a monstrously long review. So let me work on it. It says, find the equation of the line tangent to the graph at the indicated point. Your test isn't going to have any other writing but that. It's going to give you an equation, and it's going to give you a point and ask you to find an equation of a tangent line. In order to find an equation of a tangent line, I need a slope and a point. I have the point, but I don't have the slope. I need to get the slope, and I get the slope by finding the derivative using implicit differentiation and then plugging some numbers in. So my hint to myself here, it says we need both a point and a slope to find an equation of a line. We are given the point, we just need to find the slope with a tangent line. We do this by finding dy dx, and then we plugged in 2 for x and 5 for y. So I'm going to find dy dx. I'm going to take this equation, xy equals to 10, and find its derivative using the product rule. I'm going to say x times the derivative of y plus y times the derivative of x. That's the derivative of the left side. The right-hand side's a constant. It has a derivative of 0. So it's x times the derivative of y plus y times the derivative of x equals to 0. The first piece is going to be x. The derivative of y is 1. Taking a derivative with a y, you need a dy dx. And then plus y times the derivative of x, which is 1, equals to 0. Cleaning this up, I'm going to have x dy dx plus y equals to 0. I need to solve this for dy dx. To do that, I'm going to minus y from both sides and get x dy dx equals to minus y. And then I'm going to divide both sides by x. And that's going to give me dy dx equals negative y over x. That's the formula I can use to find the slope of the tangent line. So I gave myself a hint. We are given a point, we just need to find the slope of the tangent line. We do this by finding dy dx, and then we plug in 2 for x and 5 for y. So the m is going to be found by plugging in 5 for y and 2 for x. So for my equation, I'm going to have the m equals to negative 5 halves, and the point is the 0.25. And now I'm going to use the y minus y1 equals m times x minus x1 to find my equation. So my answer is going to be y minus y1, which is y minus 5, equals m, which is negative 5 halves, times x minus x1, which is x minus 2. I'm going to leave the left side y minus 5, And I'm going to clear the parentheses on the right side. I'm going to go negative 5 halves times x, which is negative 5 halves x. And then I'm going to go negative 5 halves times negative 2. When I go negative 5 halves times negative 2, the two negatives are going to be a positive. I could cancel the 2's if I'm clever, or I can consider this negative 5 halves times negative 2 over 1. And then multiply the negative 5 and the negative 2 and get a positive 10. Multiply the 2 and the 1 and get a 2. And that's 10 over 2, which is 5. So after the negative 5 halves x, I get what this reduces to, which is a positive 5. It's a positive because the two negatives cancel out to be a positive, and these two cancels and you get a positive 5. To finish up this question, I'm just going to add 5 to both sides. And my answer to question 8 is going to be y equals negative 5 halves x plus 10. All right, 2 more questions to do. So we have 2 problems left to do. Problem 9 talks about a pebble being dropped into a calm pond and it makes ripples. So a pebble gets dropped into a pond, it starts making ripples, and each of the ripples is a progressively bigger circle. I'm going to take a snapshot at the biggest circle at one point in time. So this is a picture of the pebble going into the pond, the biggest circle that it's made at the moment this word problem is being written, I guess. So a pebble's dropped into a calm pond causing ripples in the form of concentric circles. The radius of the outer ripple is increasing at a rate of 3 feet per second. That's going to be an important number. And when the radius is 6 feet, at what rate is the total area of the disturbed water changing? So there's a couple numbers that are given in this problem. And the first number I see is the radius is increasing at a rate of 3 feet per second. That tells me that dr dt, how the radius is changing with respect to time, is 3 feet per second. That's the first number that's given in this problem. The second number says when the radius is 6 feet, so when the radius is 6 feet, at what rate is the total area of the disturbed water changing? The rate where the area is changing is dA dt, and that's what I need to find. So for this particular circle, I'm said that the radius is increasing at 3 feet per second, and at the instant that the rate is 6 feet, how fast is the area changing? This is kind of an easy problem. For this circle right here, the area of this circle, it's a generic circle, its area is generically pi r squared. I'm going to hold off plugging numbers in I'm going to take the derivative before I plug the numbers in. If I plug my numbers in before I take the derivative, I'm not going to have the variables that I need to have. So I'm going to use implicit differentiation with respect to t. The derivative of a is 1. I'm taking the derivative of a with respect to t, so I'm going to tack on a dA dt. The right-hand side, the derivative of pi r squared is 2 pi r. I took the derivative with respect to t, so I'm going to tack on a dr dt. And now I'm going to plug in for r 6 feet and for dr dt 3 feet per second. So I'm going to get the left-hand side is just going to be dA dt. I don't need the 1 there. The right-hand side is going to be 2 pi, and then it's going to be times 6 feet, and then times 3 feet per second. I'm going to multiply the 2, the 6, and the 3. 2 times 6 is 12. 12 times 3 is 36. I'm going to leave the pi. I'm going to multiply the feet and the feet to get feet squared. And I'm going to leave the per second. And this tells me that the area of the pond is changing at 36 pi feet squared per second. That's the whole answer to problem 9. I don't know how good that was, but it's the 3rd time that I've done this, and it's definitely better than the last 2. If you're not happy with this explanation, ask me in class. If enough students ask me in class how to do this problem, then I'll know this is a horrible video and I'll redo it. Last problem, problem 10, gives me air is being pumped into a spherical balloon. So this is my balloon. It's the shape of a soccer ball in some sense. Air is being pumped into it at a rate of 3 centimeters cubed per second. That tells me how the volume is changing with respect to time. This first number tells me the volume is changing with respect to time at 3 centimeters cubed per second. Then it says calculate the rate at which the radius of the balloon is changing. This is asking me to find dr dt. That's the rate at which the radius of the balloon is changing. When the radius of the balloon is 10 centimeters, that tells me that the r is equal to 10 centimeters. So my goal is to find dr dt given dv dt is 3 centimeters cubed per second and r is 10 centimeters. In order to do this problem, I need to know a formula for the volume of a sphere, and I need to take its derivative with respect to time. I think I give this to you on the test. If I don't give it to you on the test, just come up, ask me in class, and I'll give it to you. So the volume formula for a sphere is volume equals 4/3 pi r cubed. I'm going to take the derivative. The derivative of v is 1. I'm taking the derivative with respect to t, so I'm going to tack on a dv dt. On the right-hand side, I'm going to take the derivative. I'm going to multiply the 3 times the 4/3 pi. I'm going to lower the exponent by 1 to r squared, and I took the derivative of an r with respect to t, so I'll tack on a dr dt. These 3's are going to cancel, and I'm going to get dv dt equals to 4 pi r squared dr dt. I need to solve for dr dt. I can solve before plugging in the numbers or after plugging in the numbers. In the last problem, I put the units in because they weren't that hard to work with. In this problem, the units would be a disaster to work with. So when I go to write my answer to this problem, I'm going to figure out in my head what the units need to be. So this is telling me how the radius is changing with respect to time. The radius is going to be in centimeters. The time's going to be in seconds. The radius is going to be growing at some rate in centimeters because that's the length. And it's not going to be square centimeters because it's not area. It's not cubic centimeters because it's not volume. The radius is changing at centimeters per second. I'm not going to put any units in here because it's going to be tough enough to follow without the units. I have my choice of doing the algebra to solve for dr dt and then plugging the numbers in, or I'll plug the numbers in and then do the algebra. For me, it's easier to plug the numbers in. So in for the left-hand side, for this dv dt, I'm going to plug 3. And in for the right-hand side, in for the r, I'm going to put 10. So I'm going to get 3 equals to 4 pi times 10 squared dr dt. This is going to give me 3 equals 4 pi times 100 dr dt. Let me come up over here and do this. This is going to give me 3 equals, I'm going to multiply the 4 and 100 and get 400 pi dr dt. And I'm going to solve it for dr dt by dividing by 400 pi. I'll divide the left side by 400 pi. I'll divide the right side by 400 pi. The left side doesn't reduce. It's just going to be 3 over 400 pi. And the right side, the 400 pi's cancel and I get a dr dt. I'm trying to find dr dt, which is the rate at which the radius is changing with respect to time. My answer is going to be dr dt as 3 over 400 pi. So that's everything we need to know for this chapter. There could be some hiccups in the video. I've made like 3 or 4 mistakes. I'm going to try to go through and cut out all my mistakes and put corrections in. If you're watching the video and there's some strangeness, let me know and I will try to fix it up.